Assalamualaikum. My name is Ahmad Shafiq bin Syed Saudi, and I am a part of the group for Group 1. So today I will make a presentation about introduction. So basically, the power system frequency is one of the most important indicator of the balance between generate power and load demand. When the electrical load increase suddenly, the system experience a power mismatch. The stored kinetic energy of rotating machine initially supply the deficit, causing system frequency to decrease. If the disturbance is not controlled, frequency deviation and affect system stability, equipment performance, and power quality. So we have the load frequency control (LFC) in this project, and multi-area system using proportional integrated derivative PID. So for the literature review, we have the literature review for the load frequency control (LFC) and also the automatic generation control (AGC). So the low frequency is a control process used to maintain the balance between generation, load demand. The frequency deviation is mainly caused by a mismatch between mechanical input power and electrical load power. If load demand increase and generation does not increase, immediately the frequency decrease. If generation exceed load, the frequency increase. LFC therefore adjust generator mechanical power through governor and turbine system. So for the automatic generation control AGC, AGC is a secondary control system that adjusts the reference power command of generator after the primary governor response in a single area system. AGC can be implemented using integral control of frequency deviation in a multi-area power system. AGC use the area control error ACE, which combine a frequency deviation and tie line power deviation. So also in this report, we are talking about the Thailand power control related to the LFC and AGC, and also PID and PI controller for approved by the calculation and the simulation by using a MATLAB. So this is the PID tuning method that we are used. First is singular nucleus, and the second one is try and error. So the problem statement is a power system load change continually, a sudden increase in load causing system frequency to drop, while a decrease in load causing frequency to rise. In an interconnected power system, the disturbance also affect tie line power between areas. So we have a 5 objective here to review the theoretical ALFC, AGC, Thailand power control, and PID. To analyze the stability of a single area thermal power plant LFC model using Routh-Hurwitz criterion to evaluate frequency deviation under different load variation in a single area system, to implement AGC in the selected thermal power, and to model two area interconnected power system and compare frequency and time response and without PID secondary control. So this is overall the methodology that we are using by using a MATLAB Simulink implementation. Step 1 is review LFC. Step 2 is build single area model. Step 3 perform Routh-Hurwitz analysis. Step 4 is simulate load variation. Step 5 add AGC. Step 6 is build two area model. Step 7 tune PI or PID control, and step 8 analyze result. So we have a single area thermal power plant here. So we have a governor, turbine, generator, base load, base frequency, operational drop, and operational gain. Routh-Hurwitz stability procedure, and we have a MATLAB Simulink implementation setting. So in the task 2, I will give to my friend, which is Ashraf, to present.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf. I will introduce our group members. First, Ahmad Shafiq bin Syed Saudi, Muhammad Anas bin Udin, Muhammad Nidil Azri, Muhammad Nazi, and Muhammad Ashraf bin Ibrahim, which is myself. This is the mini project for power system control. Title load frequency control analysis for single and multi-area using PID controller. So I will be presenting on the calculation part. Okay, so for single area LFC is under subset 5, which is single area thermal power plant LFC analysis. So the system we choose, it has the load change. We try a variety of load change. So this is the expression circuit. So we start by calculating area A and area B, and then we draw a simplified circuit. From simplified circuit, we obtain simplified the expression. We have the ni lah value of the transfer function. And then from there, we have the value. We do Routh-Lewis to get the value of K, which is 84.59. So from there, we get the value of R is 0.012. From there, we do the transfer function of closed loop circuit. From there, we get the value of transfer function, which is 0.012, T0. So from T0, we get the value of until 0.048. So from there, we get the frequency actual by multiplying PU and base into negative 0.24. So the end value of frequency is 49.06, the frequency change. So we try a different value. We try 20 megawatt, which bring the PU to 0.2, and 60 megawatt, which bring the PU to 0.6, and then we have certain value which we put in the table. Fix this. Okay, so we can see here that the smaller the load change, the smaller frequency change, the closer it is to the actual frequency of 50 Hz. So we can conclude that if the load change is small, the system is working minimally to stabilize the circuit, reduce the steady state error from 50 to bring it back to 50. Here we can see the comparison from calculation to simulation, which will be explained by my group members. We can see here that the calculation is 49.88 Hz and the simulation is 49.88 Hz also. So there is no much error. Okay, so that's all from me for the calculation parts.
Assalamualaikum, and my name is Muhammad Daniel Azri. So first of all, thank you Ashraf for your explanation before. And my part is to explain about a simulation. So moving to task 1. So our system, we are using a 1 over 1 plus 0.5 S and 1 over 1 plus 0.55 S, and also 1 over 20 S plus 2. So moving to the simulation, as you can see, you are using governor 0.5 S, and turbine is 0.55 S plus 1, also 20 S plus 2. So the key value that we get from this calculation is active 4.58. So means again 1 over 0.012, which is 8.83. So let me explain about this one. So this is the FP1. So this value we need to multiple to 50 Hertz because our system are using 50 Hertz. Then we get the F actual 1. So to get the frequency settled, this value we need to minus with the 50 hertz. Then we get the what we mean is frequency settle. So moving to the simulation output. So this is the oscillation at the Roughway stability limit K is 84.89. Sorry, 59. We get. So the conclusion that we achieve, we get from this simulation is substance sinusoidal output indicate that the gain is at the marginal stability limit. And if the gain is increased beyond this value, which is 84.59, the system would become unstable. While if the gain is below this value, the system remains stable and the oscillation will be damped. So that's for task 1. So moving to task 2, which is um, LFC stability with load variation. So actually for this simulation, load we are using is 20 megawatt, sorry, for the load. So this calculation Ashraf already explained before. So moving to the simulation, this part. Okay. The governor and turbine value the same as before, but the K is 1 over 0.12, which is still under our limit. So the value that we get is 49.03 hertz. This is the graph, the simulation output that we get. Frequency response for 20 megawatt load change settling at about 0.0023 pu and equivalent to 49.88 hertz. So the conclusion that we get, the results show that the system is stable for the selected gain, but permanent frequency drop remain under primary control. So the key point for this calculation is the larger the load increase, the larger the final frequency deviation. And this confirms that governor drop response alone cannot restore the frequency to exactly to 50 hertz. For the time taken to steady state, quite high, which is 2012 milli per second. Millisecond, sorry, to settle, to get the value of 0. So moving to next, which is LFC of selected terminal power plant using AGC. For this part, AGC loop is added to the single area LFC model using an integral controller. The purpose of the AGC integration is to continuously adjust the turbine input until the frequency error is removed. In the supply simulation, KI, which is integral controller we are using is 8.33, is added as a parallel integral loop. So moving to the simulation, as you can see in the picture, the governor turbine also steam and our load which is we are using 20 megawatt and our K we are using 1 over 0.012 while this part Ki 0.5 per S. for our integral loop. So the result that we get from this simulation is this one. But the difference is the time taken to frequency response of which is quite high. The value is 2315 millisecond to achieve zero. This is because before AGC, the 20 megawatt load change caused the frequency to settle at approximately 49.88 Hz. But after adding AGC, the integral action gradually changed the mechanical power command and eliminate the steady state error. The frequency is restored to 50 Hz. The response is slower and smoother, okay, because the integrator increase the system order and introduce a gradual correction mechanism. So this is the main reason why the time taken is quite higher than before, because our integrator increase the system order and introduce a gradual correction mechanism after we are using the KI. So that's all from me. And moving to Muhammad Anas, he will continue the presentation. Thank you.
Now I will continue to present for task B, double area. So for double area, it's under chapter 6, which is two area interconnected power system analysis for wind turbine. So this is the value we are working with. We have the load change of 300 megawatt over 100 megawatt, which bring us to 0.3 PU. Okay. So this is the calculation. First, we draw the circuit to our understanding, and then we calculate the speed regulation, inertia and load, PU load change, steady state frequency deviation, steady state frequency of actual value, which bring us to 59.64 Hz, the tie line flow, and then the mechanical power deviation change. Okay, so for mechanical power, we have 150 and 120, which bring us to 270 here. Okay, so our load change is 300 megawatt. So the excess value is calculated in the change in area. So if we total up this value, we have 8.7 for the change in area total. So 8.7 plus 270 is 278.7. It's close enough to 300. Okay. So we can see also on the table. So for frequency deviation load change in area 1, you can see that from observation of the simulation, we have 0.022, but for calculation is 0.0048. Sorry, for simulation is 0.003, negative 0.003, and for calculation negative 0.0048. So it has an error of 0.18. So good enough. And then, of course, for the theory, when we add PID, it should return to 0. So yes, the simulation also return to 0, which the simulation part, my group mate will explain about it. And then for the power deviation, for change in area 1, okay, so the observation for simulation is negative 0.09, but for theory, we have negative 0.124. Okay, so it's a change of like 0.1. And then wait PID, it should return to 0, and it does return to 0 after we add the PID, which the simulation part, the graph, everything will be explained by our group mates. And then for the change in area tu, the frequency change, the observation is 0.11, but the calculation is negative 0.155. So it got some error. Also for the width PID, the simulation is 0.23, where it should be 0. These changes may due to the round up in the calculation or error in summing up the value. So that's all from me for the calculation parts, and the other part will be explained by our group mates. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Thank you to Daniel Azri. Okay, now my name is Muhammad Anas bin Nurdin. Okay, I will present to you my part, which is task 3, two area interconnected power system analysis. Okay, first of all, I will give to you the introduction. My project is two area system specification, which is we have the two area power system consist of two control areas that connected by a high voltage tie line. Okay, each area includes a governor, turbine, load damping, and inertia block. The load change used for the analytical two area calculation is 300 megawatt at 1000 megawatt base equal to 0.3 pu. Okay, as you can see here, the table here, we have item, the area 1 and area 2, which is we have the item load damping for area 1, area 2, the inertia constant, which is H, governor time constant, which is TG, turbine time constant, speed regulation, R, and 1 over R for both area. Okay, next, as you can see here, this is a MATLAB simulating model for the interconnected two area LFC system. Okay, you can see here, which is we are using MATLAB, and I have the PID controller here, which is I only use PI. We have the the governor, the sum, the scope that calculate the frequency deviation and the power deviation. Okay, the gain symbol here, sum, and is the power given. Okay, next. I will show you my first task, which is task 3A, which is I need to find the frequency deviation for load change in area 1 only, just area 1. Okay, the first simulation case studies the frequency deviation when a sudden load increase occurs in area 1. Okay, without PID or PI secondary control, the frequency drops sharply and oscillate before settling with a small permanent error. With PI control using the trial and error method, the integration remove the permanent frequency error. Okay, why I'm using the trial and error method? Because first I tried the tuning method, but because of the licensing issue, I only can do the trial and error method. Okay, first of all, the case for the task 3A, the without PID or PI, so I control the setting for the KP 0, KI 0, and KD also 0. So for the time sampling, I set to 60 seconds. Okay, as you can see here, the simulating result here. Okay, these are the area 1 frequency deviation without PID control. Okay, so the observation frequency drops to around negative 0.022 Hz and settles near negative 0.003 Hz. I can see here first bigger oscillate, and then finally the value is negative 0.03 Hz. Okay, as you can see here, these are the frequency deviation with PI or PID control. Okay, okay, I'm setting the KP value. Actually, this is a mistake. I set the KP 0.6 and KI is 0.2 in time sampling 60 seconds. Frequency deviation return to 0 Hz by approximately after 55 seconds. Okay, let's see. As you can see here, you can see the graph, and then finally turn to 0.3. Okay, the comparison confirmed that primary governor action is able to damp the fault oscillation, but it cannot eliminate the final steady state error. The integral term in the PI or PID controller accumulates the remaining frequency error and adjusts the generator set point until the final deviations become zero. Okay, that's all for 3A. And then next, we will continue the second task, which is the task 3B, which is the tie line power deviation for load change in area 1. Okay, first, the second simulation case studies tie line power deviation when the load disturbance occur in area 1. The tie line response is important because it shows whether area 2 is permanently supporting area 1 or whether area 1 eventually supplies its own increased load. Okay, first, case here, the case without PID or PI. So KP set to 0, KI set to 0, and sampling set to 30 seconds. Okay, the observation, tie line power deviation settled at approximately 0.09 PU, indicating permanent unscheduled support from area 2. Okay, you see these are the 3B without PID, and we measure it at the scope number 2. Okay, this is the 3B without PID, which is from the we measure from the scope 3, and this one the 3B without PID at the scope 4. Okay, this one, as you can see here, this is a simulation result for 3B with PID scope 2. This one 3B with PID measure at the scope 3, and this one 3B with PID at scope 4. Okay, so as you can see here, for the case without PID or PI, we measure using a 3 scope, scope 2, scope 3, and scope 4. And also with PI and PID, we also measure using the scope 2, scope 3, and scope 4. Okay, so with PID, the observation tie line power return to 0 PU by about 50 to 60 seconds, restoring scheduled interchange. And as you can see here, okay, first of all, you can see here, it returned to 0. Okay, second one, this one also is returned to near the 0, 0.1. And this one also return to 0. Okay, so sorry, this picture a little bit late. Okay, the without secondary control, the tie line power deviation remains non-zero because the other area continue to share the load disturbance. With PI or PID action, the area control error is reduced and the local generation in area 1 increases until area 1 carries its own additional load. The scheduled tie line interchange then restore. Okay, that's for the task 3B. And next, we continue to task 3C, the tie line power deviation for load change in area 2. Okay, this third simulation case studies tie line power deviation when the load increase occur in area 2. The direction of the tie line deviation is opposite to the area 1 disturbance case because power initially flow from area 1 to area 2. Okay, this is a simulink. As you can see here, first I change this part to the sum 4. Before this one at the sum 3 connect to the sum 3. And then I replace this one to the sum 4 and change the sum plus minus symbol here. Okay, then I add the PI value here. Okay, that I setting for PI, I set 0.6 and KI 0.2. Okay. That's all the additional for one, and I will tell you the without PID or PI in area 2, tie line deviation rises and settles around positive 0.11 PU, showing that area 1 permanently export power to area 2. Okay, you can see here the result for the 3C without PID scope 2. Time sampling 60. You can see here, the finally in the straight line without scope 3, here starting from 0 and finalize at 0.13. And this one at the scope 4, the big oscillation, and then you can see here, the final value is 0.1583. Okay, that's for the without PI or PID controller. Next, with PI or PID in area 2, the observation tie line deviation spiked initially to about 0.23 PU, then gradually return to 0. PU by 50 to 60 seconds. Okay, as you can see here. Okay, with PID. 3C with PID. You can see here, it spike, nearly 0.25, and then it's dropped to near zero back. Okay, you can see here at the scope 3, starting 0, it spiked to 0.19. 3C with PID scope 4, starting 0, oscillate, and then finally got a 0.0039. Okay, so the response proof that the controller must be active in the disturbed area to restore the scheduled timeline flow. If area 2 controller is off, area 1 continue to have area 2 permanently. When area 2 PI or PID controller is switched on, the local generators increase output and the timeline deviation returns to 0. Okay, that's all from me. Thank you.
So as a conclusion, the mini project successfully analyzed load frequency control for a single area thermal power plant and two area interconnected power system. The Ruth Hurwitz criterion showed that the single area LFC system is stable for gain value below approximately K equal to 84.59. Since the selected operating gain is K is 83.33, the model operates within the stable region. The load variation study showed that primary control can stabilize the system but cannot restore the nominal frequency. A 200 megawatt load increase caused the frequency to settle at approximate 49.03 Hz. Higher load chance produce larger drop when AGC integral control is added. The steady frequency error is eliminated and the system returned to 50 Hz. So that's all for me and for my team. Thank you.